Okay, moving on to Unit 6. I know we're jumping around a lot, but Unit 6. Hey, if you open to the very first page, we're going to talk about some of the graphs that you are used to seeing and you have already seen. Okay, we have the linear graph. This is linear, plain old y equals mx plus b. Y'all have seen it forever. We've done it forever. Okay, this guy right here you may not be as familiar with. Okay, this is the absolute value. The absolute value graph. Totally running out of room there. Okay, this is a quadratic. It's a parabola. We've dealt with parabolas for a long time now. Okay, and this is the quadratic. And finally, the cubic. Okay, so anytime you see a equation with a plain old x, okay, only an x, no other exponent at all, it's going to look like this. It's going to be a linear graph. Okay, for absolute value, I know this is kind of hard to see, but anytime you see absolute value brackets around an x and no other exponents, then you are going to have an absolute value graph. If you see an equation with an x squared in it, okay, it could have an x squared, it could have an x, it could have absolute value, but if the highest exponent is an x squared, it is going to be a quadratic that looks like this. Finally, if you have a x raised to the third as your highest exponent, then it is going to be a cubic graph that looks something like this. Okay, this linear graph has a domain that goes from negative infinity to positive infinity. Okay, it never stops. When you go from left to right, remember domain is left to right, so it is going on forever to the left and forever to the right. Okay, our absolute value graph does the same thing. It goes on forever to the left and forever to the right. Quadratic, same situation. Remember, just because our graphs stop here, this quadratic graph is slowly getting wider and wider and wider, just like the absolute value is. Okay? And our cubic, getting wider and wider the further you go in either direction. Okay, if our domain is left and right, our range is bottom to top. Okay, let me say that again. Domain is left to right, range is always bottom to top. Okay, so let's talk about the range of our linear. Okay, the lowest point we ever get to on this linear graph is somewhere that we can't see. Okay, so it's negative infinity, and it gets all the way up to another point we can't see, so positive infinity. Our absolute value graph is a little different. Okay, if we get on here and we figure out the lowest point we get to, it's actually right here, which is 0. Okay, and then we go on infinitely in the positive direction. Okay, so our graph will never, in its current state, ever get below 0. Okay, with that same regard, quadratic is the same way. Quadratic and absolute value look a lot alike. This one's a curved version. This is a much sharper version of the graph. Okay, so this guy right here, he gets to 0 and all the way to infinity. And then our cubic graph is a very crooked version of our linear graph. So his range is also negative to positive infinity. Okay, all 4 of these graphs are parent functions that we've dealt with before. Okay, the linear, cubic, quadratic, absolute value, all have been seen before, I think in 9th grade. Okay, these 2 guys that we're about to throw in here are brand new. Okay, you have not seen them before. Okay, this is the square root function. Okay, so let's fill out our t-table real quick so we can see where we need to plot these points. Okay, remember, if I give you the x, you plug it into the equation, it'll give you the y. So the square root of negative 9, okay, the square root of negative 9 gives us an imaginary number. So there is no square root of negative x, or negative 9, on our square root function, which means there's no negative 4, there's no negative 1. Okay, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of positive 9 is 3. So when I graph this, it looks something like this. And it is kind of the shape of a arch. Okay, it is kind of like if you take a spoon that you're going to eat out of, okay, and you turned it the other way, you turned it upside down and removed its handle, you've got your square root function. Okay, so our square root function is kind of a hook. Okay, so let's jump down here to domain and range. Okay, my domain, remember, is left to right. So how far to the left do I go? Well, in this case, I only go to 0. Okay, anything over here, if I'm trying to take the square root of these negative numbers over here, it's going to be imaginary numbers, and I can't graph that. Okay, you can tell me that the square root of negative 9 is 3i, but you can't graph it. Okay, and then in the positive direction, as far right can I go is infinity. Okay, as far as the range for this one is concerned, the lowest point that I get to, remember range is bottom to top, so the lowest point I get to is 0. And then while it looks like this guy is going to level out, he's really not. He's going to constantly keep growing in the positive direction forever. Okay, another new guy to the scene is this cubed root. Okay, in your calculator, if you hit the math button, look right down here at number 4. Okay, remember when we did the changing the square root to exponents, and there was always an understood 2 in front of the radical? Well, in a cubed root, there's a 3 right there. Okay, so if we go down here to number 4 and hit enter, it pulls our little cubed root to the main screen. Okay, and then we can type in these values. The cubed root of negative 8 is negative 2. Okay, you can take the cubed root of a negative, it's fine. Obviously, it didn't give us an error. Okay, the cubed root of negative 1 is negative 1. Cubed root of 0 is obviously going to be 0. Cubed root of a positive 1 is positive 1. And the cubed root of positive 8 is positive 2. Okay, so let's graph these and see what it looks like. I have my negative 8. It goes with my negative 2. Negative 1 with negative 1. 0, 0. 1, 1. 8, 2. Okay, so my cube root looks something like this. Okay, if you look at it, it's very similar to our cubic function, our x cubed. Okay, he's kind of turned sideways. Okay, if you look though, the cube root function starts at the bottom, goes through 0, 0 in this little curvy fashion, and then goes off to the right. Okay, so it starts low and then ends high. Okay, if the domain of the cubic was negative to positive, and all I did was basically turn him sideways, then the domain is not going to change. Negative to positive infinity, and the range is the same. Negative to positive infinity. Okay, the next question asks, what 2 points do all 6 of these have in common? Well, they all have a 0, 0, and they all have a 1, 1. Every single one of these graphs has those points in common. Okay, all the parent graphs have the same domain. They're all negative to positive infinity except for one, and that is our new guy coming into the equation here, which is the square root function. Okay, his domain is different. Remember, we don't have negative under the radical because they're imaginaries. So he is from 0 to infinity. Okay, we have two categories for range. We have the negative to positive infinity range category and the 0 to infinity. Okay, so our negative to positive infinity range, we have our linear, we have our cubic, and we have our cube root. Again, all of these are negative to positive infinity. Then we have the other group of ranges that are 0 to infinity. Okay, and that would be our absolute value, our quadratic, and our square roots. Okay, which parent graphs have symmetry on the y? Okay, what that means, if I would take my paper and fold it in half along that y-axis, so fold it in half, whoops, right here, which ones would be symmetrical? Okay, just gave you a hint there. Quadratic is symmetrical, absolute value is symmetrical, and that's it. Okay, this guy, if you folded him over, he would not be symmetrical. Definitely not this one. And when you fold him over, it would not be either. Be mirror reflections of what's on the other side, but not symmetry. Okay, so we have our absolute value and our quadratic. Okay, then it says which ones have symmetry about the origin, meaning their corners, their opposite corners, look exactly the same. Okay, so if we look at linear, nothing in this corner, the opposite corner also has nothing. Okay, we have an arm going off here, the opposite corner has an arm going off there. Okay, so linear is one of them. Okay, we said those were symmetrical about the y-axis. Okay, opposite corners are blank, opposite corners have graph. So our cubic. Okay, 99% of the time, whatever happens with cubic also happens with cube root. And in this case, he is symmetrical across the origin. And then our poor, lonely square root function that has no symmetry whatsoever. Okay? Alright, flip it over and let's start moving some of these guys. Okay, so look at these 6 pictures of our graph right here, or 6 pictures of equations, not even pictures, they're just equations, sorry. Okay, and all of them have an h and k added to them. Okay, we remember from circles and vertex and all that stuff that h and k is x and y axis, okay, x and y coordinates. H stays with the x, k is always with the y. Okay, the function itself tells you the shape of the graph. Okay, so like we said before, if it has a squared in it, it's shaped like a U. If it has a cubed in it, it's the curly Q looking S thing. Okay, if it has the absolute value bars, it's shaped like a V. Square root symbol, shaped almost like a square root. Okay, cubed root is the cubic root turned sideways. Okay, there's other things that happen to it. Okay, if the number out in front, if you put a number out in front, okay, if it is less than 0, or if it's a negative, think of it that way, if it's a negative, it flips the graph over the x-axis. Basically flips it upside down. Okay, we dealt with that when we did parabolas. Okay, when we were graphing those focus and directrix and flipping them. Okay, if the x is less than 0, so if I would put a negative in front of these little x's that are going on inside of the equation itself, then it flips it over the y-axis. Okay, it basically makes it have y-axis symmetry if we're sitting at 0, 0. Okay, so it would take it and flip it from the right side of the graph going to the left side direction. Okay, A, the one that's either positive or negative, is the slope from the vertex to the next point. Okay, if I add a k onto the back of any graph, I'm going to move it up however many units that is. If I subtract a k, I'm going to move it down. Okay, think of it, it's a y coordinate. K is a y coordinate. Positive y, move up. Negative y's, move down. Okay, and just like with circles, if I would put a plus h, it actually goes opposite direction. Oh, this is supposed to be h. Okay, a plus h would actually move it to the left, and a minus h actually moves it to the right. Okay, so real quick, let's jump in and do some of these transformations. Okay, this guy right here is the square root graph. Okay, it is the square root graph. I don't have any negatives in front of it, so I'm not going up or down. I'm not flipping upside down. Okay, I do have a plus h in here. Okay, plus h tells me that I go left. In this case, I'm going to go left 6 units. And then I have added a k to the outside. When I add a k, it tells me to go up. In this case, I'm going up 2. Okay, I don't so much care about these situations. What I do care about is I want to see what this graph looks like. I'm going to sketch a picture of it, and then I'm going to do the domain and range. Okay? To sketch a picture, my normal square root graph starts here and goes off something like that. Okay? My new graph, where I moved him left 6 and up 2, you basically are going to take him by his nose right here. Okay, and I'm going to go left 6 units, up 2 units, and then graph the exact same thing. Okay, again, left 6 units, up 2 units, and graph the exact same shape. Okay, now for the domain and range. Remember, domain is how far to the left, and range is how far to the right. So in this situation, on the pink one, we're done with the blue. That was my original. Okay, if I go as far left as I can go on this graph, I'm going to be at negative 6. If I ride this thing to the right as far as I can, I'm going to get to go to infinity. Okay, for the range, bottom to top, the lowest I can get on this graph, remember range is y, is going to be at positive 2. And the highest I will ever get is infinity. Okay, let's look at this guy. Still the square root function, so I'm going to sketch an original picture of the square root right here. Okay, this time I do have a negative a, so that means I'm going to flip upside down. And then I have a plus k on the outside, so I'm going to go up 6 units. Okay, plus k. up 6, and I'm flipping upside down. Okay, so let's take my nose, move him up 6 units, and instead of being a nice little rainbow, he's going to become upside down like that. Okay, again, I don't care so much about these. Let's look at our domain now. Okay, domain still left to right. So how far to the left can I go? I can go all the way till I get to x is 0. And I can stay on it in the positive direction to infinity. Don't forget, range is bottom to top. Since my graph is going on forever and ever and ever, the lowest point I will actually ever get to is negative infinity. And the highest point that I will get to is right here at positive 6. Okay, here's the cool thing. If you pull out your calculator, hit the y equals button, you can type this guy in right here. Negative square root of x, outside of the radical we add 6, hit the graph button, and it will show you exactly what I just drew right there. Okay, it's a nice, pretty way to check exactly what you're doing. Okay, flip it over and let's graph some more. Okay, still dealing with the square root function. So again, I'm going to draw my square root function so you know what it looks like. Okay, this 3 right here is just going to make it taller. Okay, it's going to stretch it out. Okay, and this negative 6 moves it down 6 units. Okay, no flipping, no anything like that, so I'm going to take his nose, grab him, move him down 6 units, and I'm going to make him taller, so he's going to get taller faster, basically, is what's happening. Okay, my domain, farthest left value is 0 on the x, farthest right value is infinity. Range is bottom to top, the lowest I get is negative 6, and the highest I get is infinity. Remember, your range is always your y's, your domain is always your x's. Okay, looking at number 11, still the square root function. We're still dealing with this guy. The negative on the x, if you flip back and look, the negative on the x tells us it flips over the y-axis. So instead of my my graph pointing towards the right, it's going to flip the other way. Okay, and then it's going to go down 4. Okay, so I'm going to take him, I'm going to move him down 4, and instead of pointing to the right, he is now going to point to the left. So there's your picture. Let's check ourselves. Okay, we have square root, negative x, put out from under the radical, minus 4, and hit graph. And there he is. Okay, starts at negative 4, and he shoots off towards the left. Okay, of course, that is going to affect our domain and range. Okay, the farthest to the left we can go on the x is now negative infinity. And this time, the furthest right we get to is 0. Okay, as far as the range, the lowest point we get to is negative 4. The highest point, although it looks like it's flattening out, it's really not. Okay, the highest point is infinity. Okay, moving along. Look, we have changed functions now. We are now the cubed root function, so we got to think about what he originally looked like. Okay, it's this curly looking snake thing that crosses at 0, 0. Okay, he starts from the bottom, goes through 0, 0, and then shoots off like this. Okay, that's the original that I just drew. This one has a -6 under the radical, so that means we go to the right 6. +4 means we go up 4. Okay, so I'm going to grab him at his turning point. Okay, he doesn't have a vertex, it's a cubed root. He does have a turning point at 0, 0. Okay, I'm going to drag him to the right 6 units, and I'm going to drag him up 4 units. So now instead of crossing and making that cute little curvy turn at 0, 0, now he's going to make that cute little curvy turn right there at that 6, 4 intersection. Again, we went left 6, up 4, and he makes his little turn right there. Okay, the good thing about the cube roots and the cubic function is no matter what we do to them, these are never going to change. Okay, because there wasn't any restrictions on them before, moving them around doesn't change the fact that they don't have restrictions. Little infinity got a little crazy. Okay, let's see what happens over here. I have a negative on the outside, which is going to flip it. Okay, so instead of starting low and ending high, we're going to start high and end low. And then we move down 6. Okay, look at the difference here between this down 6 and then this one that moved us to the right 6. Okay, this right 6 was still under the radical with the x. This one is clearly on the outside. Okay, outside of the radical, up and down, inside, left and right. Okay, so again, I'm moving down 6, and instead of starting low and ending high, I am starting high and ending low. Okay? And again, the domain and range of these never changes. Going back to my old infinities, guys. Okay, flip it over. Okay, 2 more where we're actually going to graph their transformation. Okay, this one has a 2 in front of it, so it's going to become taller. So closer to the y, which is a stretch. And we have a +4 under the radical, which is opposite, so we're actually going to go to the left 4. Remember, we're still dealing with the cubed root. Okay, so I'm going to go left 4 units. And he becomes taller, so he looks something like this. Okay, again, the good thing about cubed roots, domain and range are super easy, never change. This one, -3 in the front. So he flips and he stretches. Okay, remember, in order to flip the cubed root, instead of starting low and ending high, we're going to start high and end low. Okay, let's see what this guy looks like in our calculator. Y equals, go into math to get that little cubed root, down to number 4. Oops, there's actually a -3 first. -3, then go into math and get number 4. Cubed root of x, hit graph, and there he is right there, slowly but surely. Okay? Okay, last ones for today. Okay, we are going to start actually writing the equations instead of graphing them. Okay, so now we have to ask ourselves, what did they do to this graph in order to get him where he is? Okay, first of all, he is the square root function, so go ahead and draw yourself an original sketch. Okay, remember the original starts at 0, 0, so this guy went to the right one, and then he went up 2. Okay, so we have y equals. In order to go to the right one, we actually are going to put a -1 under the radical, and then up 2 is a +2 on the outside. Again, there's my original. This guy went to the left 2, and then he was flipped. Okay, remember, square root function. In order to flip the square root function, he gets a negative on the outside. And to go left 2, we actually add 2 under the radical. Okay, last one for today. Again, let's draw our original so we can keep an eye on what happened to it. Okay, he went left 1 unit and he got taller. So for the point of this exercise, let's just make up a number. Okay, so let's say he was stretched. Okay, I don't want to stretch him too far. So let's say he stretched 3 units. Again, it's the square root function. He went to the left 1 unit, which means we actually add 1 under the radical.